So I'm Nicolau. I work at ECMWF as an analyst, and I'll show you the work that we are doing together with the EPCC at the University of Edinburgh and with the help of the DAOS team to assess DAOS as a backend for our fields database. ECMWF stands for European Centre for Medium Range Weather Forecasts. We are a governmental organization. We do research on numerical weather prediction, but also we are a 24/7 operational service with the duty to deliver numerical weather forecasts to cooperating and member states. We run numerical weather prediction simulations at diverse resolutions in our supercomputer. And just a second, yeah. We run the model in the supercomputer 4 times a day in 1 hour time critical windows. We have 4 of these windows. And during each of these 1 hour time critical windows, we generate about 40 terabytes of weather fields, which we store and index in a hot layer storage called FDB. That's the fields database. And we also access these fields from the supercomputer to generate derived products. FDB is a domain-specific object store developed at ECMWF, and it is currently deployed on top of a Lustre file system, which we use for indexing and the storage of the weather fields. Here, this is a diagram to stress the object store semantics of FDB. When you want to store a weather field, you need to provide a string of characters with a set of key value pairs identifying the field. The field is stored and indexed with that string of characters, and then when you want to retrieve the field, you need to provide the same set of key value pairs. I said that we are generating about 40 terabytes per hour now, but the prospect is to generate about 180 terabytes towards end of next year, and about 700 terabytes in the next 2 to 4 years. So we really need this FDB object store to scale, and for that we need to consider new technologies such as object storage and storage class memories, and that's why we are assessing DAOS as a potential backend for FDB. Of course, if we want to test DAOS, we need a platform where we have storage class memory. And this platform is the Next-Gen IO platform hosted at EPCC at the University of Edinburgh. It is a 34-node cluster with Intel Xeon dual socket CPUs nodes and OmniPath interconnect with dual rail. Each node has 3.2 terabytes of Intel's Optane DCP-MM and 192 gigabytes of DRAM. Worth noting here that we don't have NVMe in our setup. So once we got DAOS deployments working both on local VMs and on Next-Gen IO, we started working on a set of C functions to perform field input and output from DAOS in a way that complies with the requirements of FDB and of our numerical weather prediction use case. You can see on the diagram on the right how we use the different DAOS concepts and objects to implement our field storage. Worth noting that we are using 2 DAOS high-level APIs, namely the key value API and the array API. And also worth noting that there are a number of containers and objects involved in our storage, which can seem like a lot of overhead, but also that's needed in order to reduce contention on a single container or key value, and also in order for the storage to scale or to implement different parts with different technologies. So once we had these FieldIO functions in place and we could verify that the DAOS APIs offer us enough features to implement what we need to do. We started thinking about performance and scalability tests, and we did some brainstorming to come up with different benchmarks that we could potentially use to assess performance of our DAOS system. And these different benchmarks are listed here in this table, from less software complexity to more software complexity. We could start with iPerf and then PI tests to check network bandwidth. Then we could use DAOS self-test and DAOS perf to check performance of DAOS at a very low level. Then we could also use IOR to check ideal application performance. We can use IOR in two modes, with segments, that is having different blocks or segments of data written as part of a single transfer, the single open and the single close for all of it. Or we can use it in repetition mode, where we have a transfer for each block or piece of data that we want to write or read. And that has an open and a close for each part. Then we also thought we could use the FieldIO library that we had developed. And we can use that library in three modes. One would be with simplifications, so that we get rid of most of the overhead from the multiple containers and multiple objects used there. And also in synchronized mode, so that we come closer to what IOR does. It works in synchronized mode as well for all the IOs across clients. Then we could use the FieldIO libraries with simplifications, but without synchronization, so that we are one step closer to our real use case. And then we can use the FieldIO functions as they are, without simplifications and without synchronization. And that should give a good idea of whether the performance is good for our numerical weather prediction use case. Finally, we could use another benchmark, which is called FDB Hammer, which is a software that reproduces IO workloads, similar in a way similar as is done in the numerical weather prediction simulations. I've marked in green here the ones that we are currently assessing, and in yellow the ones that we will assess later on. You can see on the x-axis of this table, we are also considering different access patterns, which I'll describe later. Also, you have here on the right a table where we list different metrics that we plan to collect for all of these benchmarks. These are fundamental metrics which will help us compute different scores or throughputs to quantify the performance of our benchmarks. These are the different access patterns considered. They have arbitrary names. 0A is an access pattern where a number of parallel clients do a write of a single object. They all write to the same object or index entry. So there's a lot of contention. 0B is the same, but they write or operate with different objects or index entries. Scenario 1 is where we have a large number of clients performing each a bunch of writes to different objects or index entries. Then there's a barrier, and then we have all those clients performing corresponding reads from the objects that they've written. But that's not quite similar yet to what we do in real numerical weather prediction simulations. So that's why we have scenario 2B, where we have half of the clients performing writes and the other half of the clients performing reads. Just to expand on the test domain, just mention that for all that table of benchmarks and access patterns that I've shown, for each of those tests, we can vary the object class used for the different DAOS objects involved. We can vary the number of client processes per client node. We can vary the number of client nodes, and we can vary the number of server nodes. If we add to this the fact that there are several parameters to be adjusted on the server and on the client side, then the test domain becomes huge. So what we have done is we have tried to fix some of these parameters with a reduced configuration with 2 server nodes and 4 client nodes. And then from then on, we have started varying parameters along the other dimensions to see where we get best performance. On specific setup, for the OFI provider, since we have an OmniPath interconnect, we first tried to use PSM2, but it was not working well with more than one DAOS server node. So we finally went for TCP. We know it's not ideal. If we have time in the future, we may try again PSM2. We know there are some recommendations for Cornelis networks for having TCP optimized over OmniPath, so we might try that as well. And we know there's an OPX provider coming in OFI, which might as well provide good performance. So we are looking forward to that. Also, quick mention to this server variable called DAOS MDCap, which we are now setting to 2048. The default, I think it's 128 or maybe 1000 something, 1024. We have seen that increasing this value helps reducing the frequency of some errors on the DAOS server side when doing massive container and object access. This variable, modifying it in DAOS 1.2 did not have an effect, but now in DAOS 1.3.106, we see it has a good result. Now, regarding dual rail, we have on each node we have 2 engines, one engine bound to each OmniPath interface. We have to set fabric interface port to distant port numbers so that we avoid collisions. We have tried hyperthreads with no effect. It doesn't matter whether we enable it or disable it, but we have seen that it is necessary to set pin num node to the corresponding socket for best performance. On the client side, we have seen it's very relevant to pin half of the client processes to each socket. Otherwise, there's a huge drop in read performance down to 10%. Also, we have to be careful with the OFI interface variable, because if you do proper pinning, but you set this variable, then all the client processes will be directed to that same interface that you have specified in there, and your pinning will be useless. So worth taking into account. Here is a table, a quite complex table of testing results with IOR with access pattern 1, testing different numbers of server nodes and engines per server node, and so on, and then also varying number of client nodes. What I want to show here is that when using a server with a single engine bound to the first socket interface and using 2 interfaces for the client nodes, we get up to 3 gigabytes write and 7.5 gigabytes read, which is not bad considering that we have a non-RDMA fabric provider. But it's curious to see that when we move to the second socket with single engine, we get half the performance. So we suspect we have a network configuration issue here. We need to explore more to see what's going on in here. Then when we use both engines on the server side and 2 interfaces per node on the client side, we get up to 5.5 write, which is a bit more than the sum of the separate interfaces, and 9.5 read, which is, I think, a bit less than the sum. Then the rest of this table is showing how the bandwidth scales as we increase the number of server nodes, each server node with 2 engines and 2 interfaces. And it's good to see that it increases linearly, although the slope is less than 1. We are happy to see that increase. Now, this is results of testing with IOR with the different access patterns mentioned before, and with different object classes. basically here we see that S1 is suitable for access patterns where the different clients access different objects, and SX is good for access patterns where the different clients access the same object. Well, particularly here we are looking at now. I'll skip this one. These are results with FieldIO benchmark. So these are our C functions using the DAOS C API. Also using different sets of object classes for the different objects involved in our design. And it's harder here to take a conclusion at this point. Maybe we see that SX for all objects performs better in test scenarios 1 and 2B, which are the ones most relevant to our use case. But still, it's not a clear conclusion. And we also see that the bandwidths are very low compared to the IOR bandwidths by maybe an order of magnitude. So we are currently exploring why this is the case. We have to mention we are computing bandwidth in a slightly different way because FieldIO is not synchronized and IOR is synchronized. So the way of computing the bandwidth varies a bit, but still we don't see why there should be such a gap in bandwidths. A good sign we see is that the latency of the FieldIO operations is about 0.06 seconds, whereas the latency in the IOR operations from array open to array close is 0.04 seconds. So in terms of latency, there's not a huge difference. So this makes us think that we are doing something wrong somewhere else, but still that's work ongoing. Now, we also took a look to the different IOR APIs that are implemented. These are results with dual rail. We see there's a lot of variation across APIs. And give me a second. Yeah, and but generally we see that DAOS performs better than the rest, except for DFS in this use case here. But generally, when we were testing with a single rail, we were seeing smaller gaps, and the results from single rail were that DAOS is a bit better in all access patterns. DFS is a bit worse than DAOS, and then PIIO is about the same as DFS, if maybe a bit lower. Yeah, then here I'm showing some heat maps of bandwidths. In this case, they are with IOR with access pattern 1 using segments mode. That is a single open and a single close for a bunch of pieces of data to be written or read. We see that, well, also worth mentioning that this is a 2-server node setup. And here on the x-axis of the heat maps, we vary the number of client nodes employed. And on the y-axis, we vary the number of clients per client node. We see that with IOR with segments mode, we reach up to 10 gigabytes, 11 gigabytes per second for write, and up to 18 or 19 for read. When we go to IOR with repetitions, that is with the no object open and object close for each piece of data, it goes down to about 50% for write and 50% for read. Then this is results with the FieldIO benchmark, the simplified version. We see that there's a substantial drop down to 10% for write and 20% for read. As we say, we are still investigating. We hope to see larger, higher bandwidth in here after we address some of the configuration issues, hopefully. And this is finally the results with the FieldIO benchmark without simplifications. The result to see here is that they are quite close to the version with simplifications, right? So hopefully our implementation doesn't add a lot of overhead. That's it. The takeaway here is that the preliminary results are good. We see that the API is fit for purpose, and the performance obtained with IOR so far is encouraging. We see the bandwidth scales with the number of servers, so that's good. There's a lot of effort required to optimize the configuration of the servers and the clients, so that's worth taking into account. And yeah, there's ongoing work to understand and potentially reduce the performance gap between the IOR benchmark and the FieldIO benchmark. That's it. Thanks for your time.